It shouldn't be taking more than a semester or even 2 semesters or more at the junior level of abstract algebra or even higher to understand a basic example of why polynomials with degree 5 or higher can't generally be solved by formulas, as opposed to quadratic equations, cubic equations, and quartic equations, which have their respective formulas: the quadratic formula, the cubic formula, and the quartic formula. In the 1830s, Évariste Galois noticed a connection between the symmetries of certain objects, such as the equilateral triangle shown below, and the roots of polynomials. As you can see, the labels are B1 at the top, B2 at the lower left, B3 at the lower right. And by symmetry operations, I mean an operation such as rotating the triangle counterclockwise by 120 degrees, pushing, that is, the label B3 up to B1, B1 down to B2, and B2 over to the side where B3 is. If I label that operation by C, then I can apply C again, or C squared, as a rotation counterclockwise by 240 degrees, pushing the symbols around again. There are 3 diagonals. I labeled those B1, B2, and B3, and we can imagine reflecting about these diagonals. This leads to a multiplication table where we can do, say, the operation B1 times B2, in which case, in standard notation, that means we do B2 first, and then we do B1, and if we do that, we see that we would arrive at the element C. So you can either do B2 followed by B1 to obtain C, or just do C. And this is a multiplication table. It has properties such as it has a 1. It's the operation that does nothing, rotate by nothing. And if you rotate by 120 and then by 240, C times C squared, say, you get back to having rotated by nothing. The rotated by nothing operation is called the identity, and addition we call that 0, and multiplication we call that 1. Every element in there has an inverse. If you go to any row, say we go to the row that contains B2, we see that B2 times B2 is E, so that B2 is its own inverse. The inverse of C squared is C, and the inverse of C is C squared, because 120 followed by 240 is 360, or 0, and 240 followed by 120 is also 360, which is 0-degree rotation. Now if you look at the equation up there, the cubic equation, x cubed minus 1 equals 0, it has 3 roots, one being 1, and then you have 2 complex number roots, x2 and x3, and they're shown in a graph which I got from Wolfram Alpha. Notice that if I sum x2 plus x3, I get the negative of x1, and algebra doesn't care if I had done x3 plus x2. So there is a invariance. I can swap symbols 2 and 3. Similarly, x1 and x3 is the negative x2 root, and x1 plus x2 is equal to minus x3. Also, x1 plus x2 plus x3 is equal to x2 plus x3 plus x1. I could have also set x1 plus x2 plus x3 to be x3 plus x1 plus x2. If you really stop and take a moment to think about this, I'm not doing anything different for the 3 roots of the cubic equation than I was doing for the equilateral triangle below. I'm applying operations that leave the triangle invariant. Supposing I were ignorant of the table down below, and I call the first one up there, the swapping of symbols, x2 plus x3 gives me negative x1. I call that P1, and the operation that swaps 1 and 3, I call that P2, and the operation that swaps 1 and 2, I call that P3, and the operation that swaps the order 1, 2, 3 down below with 2, 3, 1, I call that P4, or 1, 2, 3 with the operation that swaps it to 3, 1, 2, if I call that P5, and I add in the operation that does nothing to the roots, no swapping of the symbols, I'd obtain the table on the right-hand side. The labels are different, and there's a rearrangement, but if you spend enough time, you'd see that they're identical to the table below. So this is the key idea, noticing that the roots of polynomials have symmetry operations which can correspond to the symmetry operations of abstract ideas such as the group of the equilateral triangle below. So what this presentation is going to show is that there are certain properties of groups of order 5 or higher that will preclude the associated polynomials from having a formula that's based on plus, minus, times, divide, and extraction of roots of its coefficients. As a quick summary, here on the second frame, I highlight the group of the equilateral triangle. For historical reasons, some people call it D3 and some people call it D6. And I highlight there in bullet form all of the properties that it takes to become a group. It's a set of elements with an identity that's closed, where every element has a unique inverse. And in the shaded area is a subgroup of the group D3 or D6. And it has three elements. It has the identity element, the element C, and the element C squared. They themselves form a group, which is a subgroup of the bigger group. This group in the gray is order 3, that is to say it has three elements. There are several other, in fact there are three other subgroups. The subgroup that has E and B1 is all closed onto itself. The subgroup E and B2 is another closed one, and the subgroup E and B3 is another closed group, and those groups have order 2. Finally, the trivial group, which is just the identity. It's a set that's not empty. It has E. E is its identity. E is its own inverse. The algebra is closed. Understanding the subgroup structure of a group is going to be critical for understanding why polynomials of degree 5 or higher do not have, in general, formula solutions. Now, before you get too far into the video, it's intended that you pause it as necessary and that you review it as many times as necessary. All the steps are included. I'm going to continue to build examples that you would have picked up in high school algebra, and in parallel to that I'm going to build the minimal algebraic machinery you're going to need, which is 2 theorems. Let me say this about the theorems. They're pretty detailed in their proof. If you can try to understand what they're saying and press on to the examples, you can always loop back to the theorems. In this third frame, you're going to see that I arbitrarily picked 4 roots to some quartic polynomial. In fact, I picked square root of 2 plus square root of 3, and then I started changing the signs that can precede the radicals. The next one, x2, has a negative preceding square root of 3, then it's preceding the square root of 2 in the third root, and it's negative for both radicals in the fourth root. And let me show you that if I take the plus or minus square root of 2 plus or minus square root of 3 and square it, I'm going to get 5 plus or minus 2 square root of 6. Let x squared be that and square it again, and I obtain a quartic polynomial. X to the 4th minus 10x squared plus 1 is equal to 0. You explicitly see how we obtain this polynomial from its roots. Generalizing this idea, say if I'm given 4 roots, I can always find the polynomial that corresponds to it. And with the equation p of x is equal to some number, times the product of a bunch of linear factors, x minus the first root, x minus second root, x minus third root, x minus fourth root, that is. If I were to work out the algebra, what I would really see is that if I do that multiplication above, say for n terms, not just necessarily for 4 terms, I'm going to get x to the nth minus sigma 1 x to the n minus 1 plus sigma 2 x to the n minus 2, all the way to my constant term, which is negative 1 raised to the nth power times sigma n, where sigma sub 1 is the sum of all the roots, sigma sub 2 is the sum of all possible products of the roots, and with ordering, and sigma sub r, somewhere in the intermediate stage, is the sum of all products with r terms, and finally sigma sub n is the product of all the roots. The first thing I would do is plug and chug and see if indeed it works for my example. If it doesn't work there, then I have problems. And so I take the four roots that I had from the previous frame and I add them up and I get 0 for sigma 1. I form the sum of pairs of products, ordered products, and I get negative 10 for sigma sub 2. For sigma sub 3 I get 0, and for sigma sub 4 I get 1. In other words, I get x to the fourth minus 0x cubed minus 0x squared plus 10x plus 1. Formulas have reproduced the quintic polynomial that I chose. Notice again that there appear to be symmetry properties that normal people wouldn't go looking for. That the product x1, x2 equals the product x3, x4. I can swap the symbol 1 with symbol 3, the symbol 2 with symbol 4, and I still get negative 1. And similarly with x1, x3 times each other is equal to x2 times x4 is equal to 1. The sum x1 plus x4 is equal to the sum x2 plus x3 is equal to 0. There is a notation and a way to generalize these observations, which I proceed to do. We're going to be studying something called permutations and groups of permutations. To keep things notationally simple, let's relabel the roots x1 through x4 by the first four integers, 1, 2, 3, 4. Let's define E as the permutation that does not do any swapping of the roots. In that yellow blob up there, it has 1, 2, 3, 4 on top, and the way I would read it is that 1 goes to 1 below, 2 above goes to 2 below, 3 above goes to 3 below, 4 above goes to 4 below. Okay, I just noticed that I also call E P1, so apologies for that, but E is P1. Now I'm going to define the permutation P sub 2 with the second yellow blob, with the 1, 2, 3, 4 on top, and the mappings below. So 1 goes to 2 below, 2 above goes to 1 below, 3 above goes to 4 below, and 4 above goes to 3 below. This captures that observation that x1 times x2 is the same as x3 times x4, both being equal to negative 1. The permutation P3 captures the fact that x1 times x3 is the same thing as x2 times x4 is 1. And there it is in permutation notation, 1, 2, 3, 4 above. 1 above to 3 below, 2 above to 4 below, 3 above to 1 below, and 4 above to 2 below. Finally, P4 encodes the other invariance, the one that has a sum, x1 plus x4 is the same thing as x2 plus x3. So 1 can go to 4, 2 can go to 3, 3 can go to 2, and 4 can go to 1. And if we start performing products of pairs of these permutations, we get that table below. It itself is a group. You can check to see if it has all the group properties. Its size or order is 4. It's usually denoted by V. It has 3 subgroups of order 2, the subgroups being 1, 2, 1, 3, 1, 4. It has the trivial subgroup E, or P1, or the set containing 1, and it's a size 1. And you'll notice when you have subgroups that the size of the subgroup divides the size of the group. Everything can be said, can be expressed through a diagram with the group V on top and arrows going down to its subgroups of size 2 and those going to the ultimate trivial subgroup 1. Here's a definition that's very important. A group is called solvable if it has a composition series or a tower in which each factor, in this case 1, 2 or 1, 3 or 1, 4, and then down to 1, is a cyclic group of prime order, ending in the identity. So in this case, V meets the definition, V is solvable, and by cyclic group I mean a group that goes all the way around and back to itself. Back at the equilateral triangle, if we rotate it by 120 degrees, and then again by 120 degrees, we go to 240, and then again by, which is C2. So C, rotate by 120 degrees, gave us C2. And if we apply C again, we get 360 degrees, and we've come back full circle. That's a cyclic group. Every element of that group of rotations by 120 degrees, 240 degrees, or 0 degrees can be obtained by repeated multiplication. So, that's something to contemplate as you pause this video and make notes. Some notation is needed below. So that funky Q symbol is the symbol that represents the rational numbers. P divided by Q, Q cannot be 0, and P and Q being integers. It's associated with it are the usual addition and multiplication of fractions. And of course you cannot divide by 0. The field of rational numbers is a set that is contained in the field of real numbers, and the real numbers contains things like square root of 2 and pi, which cannot be expressed as fractions. And the field of real numbers itself is a field that is contained in the complex numbers. So to clear this up a little bit, here's a trivial polynomial. X minus 1/2 is 0, its solution is 1/2, and that happens to be in the rational numbers. But now consider this polynomial that has x squared minus 2 times x squared minus 3. And the roots are plus or minus square root of 2 and plus or minus square root of 3. Those numbers are not rational numbers. We can, however, extend or grow the field of rational numbers to a new field, a field extension, that would have those numbers. And for instance, we can say Q with parentheses square root of 2 inside is equal to the set A plus B, those being rational numbers, with B times the square root of 2. Say 1 plus the square root of 2. That's an element of this field extension. We would proceed with this field extension methodology, adding square root of 3. And so the numbers in that field extension with square root of 2 and square root of 3 would look like A, B, C, D, all coming from the rational numbers, with B times the square root of 2, C times the square root of 3, and D times the square root of 6. That set right there is big enough to contain the solutions of the polynomial above. Again, continuing with the group idea, let's have in the table below square root of 2 and square root of 3 mapped to themselves, S1, or mapped to minus the square root of 2, square root of 3, that would be S2, or mapped according to S3, or mapped according to S4, where we have square root of 2 mapped to its negative and the square root of 3 mapped to its negative. If you start forming products of these, you will notice that they form a group. Now in this next frame, I want you to notice that with the field extension Q at the bottom right, we can extend it by square root of 2, or by square root of 3, by square root of 6, and we move our way up to square root of 2 times square root of 3. It has a parallel structure to the group V, which goes from the group V to its subgroups 1, 2, 1, 3, 1, 4, and up to the trivial subgroup, the identity. We are within 2 frames of showing you why problems are going to happen with trying to find formulas for quintic polynomials or above. And the figure on the right hand side is extending the field of rational numbers so that it's big enough to have solutions to a quartic polynomial, the one above the previously presented, and it happens to be identical to the structure of the group V with its subgroups. The diagram on the left-hand side doesn't know anything about polynomials. It's just a symbol swapping algebraic structure, which may correspond to some geometric figure like the triangle, or simply to some abstract table that satisfies the definition of a group and it has no geometric picture associated with it. Let's add the final round of necessary algebraic verbiage. The object in bullet 1 there, Q with square root of 2, square root of 3, that field extension is specifically called the splitting field of that polynomial, x squared minus 2 times x squared minus 3 equals 0. It's called the splitting field because it splits up the polynomial into a product of 4 linear factors. X plus the square root of 2, x minus the square root of 2, x plus the square root of 3, x minus the square root of 3. For groups in which you can do the ordering in either I, J, or Ji, you call that commutative, where we've known this property since we've learned to multiply. 5 times 4 is the same as 4 times 5. Not everything is commutative. The vector cross product is anti-commutative, that is A cross B is equal to the minus of B cross A. The group of automorphisms, the group of swappings, if you will, of the roots, that is called the Galois group. And it has this notation that looks like a fraction. of the field extension over the rational numbers. And finally, at the last paragraph, we all know that the square root of 2 is an irrational number. It's not expressible as a fraction, as such as being a solution to a polynomial. X squared minus 2, it's called an algebraic number. The number pi, on the other hand, isn't irrational. It's transcendental. It can't be expressed as a finite collection of numbers. You need an infinite series to define pi. And then we have the mod notation there. We're familiar with it. If we use AM, PM, we know that when we go from 11 AM, say, plus 2 hours, we're not at 13 AM, we're at 1 PM. Here in this case, 6 is congruent to 1 mod 5, means that if you move the 1 over, 6 minus 1, that result is divisible by 5. Now we obtain a word-based preview of why quintics or polynomials of degree higher than 5 can't generally be solved by a formula. Okay, we've connected the roots of a polynomial to its coefficients. We need to go the other way around. We need to connect the roots of a polynomial to its coefficients. This is what we normally do. If I give you a quadratic equation, you use the quadratic formula of its coefficients to obtain the roots by multiplication, division, subtraction, addition, and the extraction of square roots. First things we'll need to show is that if we have relationships like x1, x2 is equal to x3, x4 is equal to -1, and that's a relationship among the roots, then there will also be relationships tying the coefficients together. And conversely, when the coefficients aren't correlated to each other, we'll show that if the roots have no algebraic relationships, there's nothing like x1, x2 equals x3, x4 is equal to -1, then the coefficients themselves will have no algebraic relationships. And then in that case, the Galois group of a polynomial will be isomorphic, or the same as the group of permutations on n symbols. Literally, that is the group of swapping symbols with, say you have n symbols. So if we have the set A, B, C, D, E there, there's 120 ways to swap symbols, or 1, 2, 3, 4, there's 120 ways to swap those symbols. And if you start forming products of that, you will see that that is indeed a group, and it's called a permutation group. And if it's of size 5 or greater, it's not solvable. That goes back to that definition of solvable being a property of a group having cyclic subgroups that go all the way down to the identity. So then I'm going to pick a specific example, x to the 5th. It's a quintic, minus 6x plus 3 equals 0. And I'm going to show that its Galois group is the same as S5, and hence that's not solvable. There is no way to connect the coefficients, that the 1 there for x to the 5th, 0 for x to the 4th, 0 for x cubed, 0 for x squared, minus 6 for x, plus 3 for the constant. There's no way to combine those coefficients by addition, subtraction, multiplication, division, extraction of square roots, extraction of cube roots, to obtain the roots. Whatever the roots are of that quintic, some of them are not expressible as functions of the coefficients. So the theorem right here, this is the first of 2 theorems that are necessary, connects roots of polynomials to their coefficients and shows exactly when the group of polynomials, when the group of the polynomial is isomorphic to Sn. I think it's 3 frames for the full proof of it, full step-by-step. You should check it fully at some point. For now, if this is your first time, then read over it and understand it, so that you can press on to the examples that will prepare you to come back and understand the theorem. Suppose the coefficients from C0 through C to the n minus 1 are algebraically independent. There's nothing connecting them over some field, say the rational numbers. The group of the equation, x to the nth power plus x to the n minus 1 with coefficients c sub n minus 1 all the way to the constant term c0 is 0, is then the symmetric group Sn. Okay, so if the coefficients aren't algebraically related in any which way, then neither are the roots. Okay, I think you can read the first 3 steps that will outline the proof, and I think those are what correspond to the next 2 or 3 pictures. You know, first we show, and I'll let you read bullet 1. Second, we show that, and finally, if there's no step 3, if there's no relation among the roots, then the group has to be the permutation group Sn. Okay, I'm just going to show you this is the first page of the proof. It's all inclusive. Here's the second page of the proof, and I think that's the end of the proof down there. So you need to check it step by step. Finally, we get to the second proof, and again, same thing applies. Understand it eventually, but please see example first. And this is just going back to the group Sn, which doesn't care about the existence of polynomials, which is a symbol swapping group. If the order of Sn is 5 or greater, then it is not solvable. Go back and review the definition of what a solvable group is. And the proof is right here. And I suggest you struggle with this proof, because this is going to show you why, if you have a group Sn with n greater than or equal to 5, and you start trying to build a tower down to the identity, you can't get to all the way through. Okay, so here's the first quintic polynomial out there that is easy to show, that can't be solved by some quintic formula. X to the 5th minus 6x plus 3 equals 0. If you go back to some honors algebra at the high school level, something called Eisenstein's criterion, you can see that for the reason cited there, prime number 3 divides the coefficient C0 but not C1, C0 on C1 but not C2, nor does 3 squared divide C0. Then we know that it's irreducible over the rational numbers. You can look this up as a definition. Again, this is stuff that you would see in an advanced algebra class in high school. Using first semester calculus, we're going to use a first and second derivative test to continue learning about the roots of this polynomial. Finding where the first derivative is 0 gives us those results highlighted in yellow. And using the second derivative test, we continue to learn about the graph or structure of this polynomial. Again, using the intermediate theorem of calculus, we're just plain graphing. And combining everything that's on this page, we see that this polynomial has 3 real roots. So that means that there's 2 complex roots out there. And with a little bit more work in the next slide, page 2 here, by taking the intersection of the field, of the splitting field with the real numbers, making x minus complex root 1, x minus complex root 2 into x squared plus ax plus b, we can see that the complex roots that must be roots of this equation are complex conjugates of each other, and they form a cyclic group of order 2 under conjugation. If you take the conjugate of C2, you get C1. If you take the conjugate of C1, you get C2. So that's a 2 cycle. And 2 cycles have that group structure of 0, 1, mod 2. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 2, which is the same thing as saying 0. And we can take the symbols 1 and 2 and keep them the same, or flip-flop them to 2, 1. That's the same group structure as the Z2 up there with 0 and 1. And if we continue to read the bottom paragraph, the logic is worked out that there must be a 5 cycle among the real roots. Just pick any one of the real roots. So what this next frame shows on this page 3 is that if you have a 2 cycle, an element that's a 2 cycle in a group, and an element that's a 5 cycle in the group, that you can basically generate every element of the group S5. I'll let you read through the details there. And if this proof is visually unsatisfying at first, keep going through it, but also press on to the next slide. And let's think about this language. Let's think about what the quadratic equation means in this verbiage. Quadratic equation there is a x squared plus bx plus c is equal to 0. We know there's a number delta squared is equal to b squared minus 4ac, where a, b, and c are rational numbers. In the example there, x squared minus 2 is 0. The field extension would be q with the square root of 2 being all numbers, a plus b times square root of 2 with ab being rational. That's this field extension. The Galois group is Z2, that one from the previous slide with zeros and ones, under addition mod 2, with the normal subgroup, or the subgroup down there being the identity. And then the quotient or factor group, Z2 over Z1, is divided by 1, you get back to Z2. And since the order of Z2 has two elements, there is some number alpha, so that alpha squared is rational. In other words, the square root of 2, when you square it, you have a rational number. For the cubic polynomial, the Galois group is S3. It has the following structure. Subgroup Z3, subgroup 1. Let's look at the ratio of S3 to Z3. That if you work out the algebra of that, that's Z2, it's order 2. And so immediately that tells me something about the field extension. It's of order 2, so there's some element, just like in the quadratic, some element alpha squared, so that alpha is part of the field extension. So if alpha squared is 2, then alpha would be square root of 2. And you need to add that extension to have that root. Now, since Z3 over 1 is Z3, that's of order 3, then we know that there is some number in the field extension, some number beta, so that when you cube it, it's a rational number. And since we can do this, we can extend the rational numbers to include all the roots of the cubic. For the quartic, it has this tower S4 to A4 to Z2 by Z2 to 1, to the identity. And you look at the first ratio, S4 over A4, that's of order 2, so you know there's going to be something, a number like 2, alpha squared, so that its square root of 2 is in the field extension. The next ratio is A4 to Z2 by Z2, and that's Z3, so that tells us that there's a number that if you cube it, it's rational, and so it's going to be in the field extension. And then you have Z2 over Z2 by 1. That's like having a pair of numbers, gamma squared and delta squared, so that gamma and delta are in the field extension. And it's the splitting field, and there is, I think the parentheses just explain that there's one element for every case of Z2. And so we can extend the rational numbers to include all the real roots, so all the roots of the quartic. And for the quintic, at the top of the tower, the splitting field is some number alpha, beta, delta, gamma, and omega, extending the rational numbers, so that it contains all the solutions to a quintic polynomial, the general quintic polynomial. The problem is explained there that if we have complex roots and they're connected to each other as a two-cycle by complex conjugation, which happens, I showed you that example. And one of the roots is a cycle of order 5, and we immediately know that its group is isomorphic or the same as the group S5, and we can't get to the intermediate field extensions by radical extension. This is really based on understanding the second theorem. So references to this are that textbook right there by Gall, and I strongly suggest you watch, I think it's the first 9 hours of lectures of this junior level abstract algebra course by Matthew Salamone at Bridgewater State University. He has a great YouTube.